It was hoped that lunar rocks would help solve that mystery. The Apollo 11 mission in 1969 marked the beginning of direct human exploration on the Moon. During 6 missions, 382 kilograms of lunar rock were collected. Transporting all that from far-flung locations on the Moon's surface required a lot of power. Apollo 15 finally developed the answer: the Lunar Roving Vehicle. Moving about freely on the Moon's surface, this lunar rover could take astronauts farther afield than they could go on foot. However, developing the rover was very much a matter of trial and error. The lunar soil would be very different from Earth's. Engineers had to develop a vehicle that could operate on all kinds of terrain. Weighing just 200 kilograms, but capable of carrying a 500-kilogram load. A supercar that would be used to locate and transport rocks on the surface of the Moon.
It was a great vehicle. They did a wonderful job in building it, you know, especially for those days. It's hard to believe now. We're talking how long ago? 40 years, 30 years? What are we talking, you know?
The last flight in the Apollo program was Apollo 17. On this mission, NASA finally included a scientist astronaut. This was a final chance to investigate on the Moon's surface, a gamble that they could discover lunar materials of types never found before.
Hey, there is orange soil. Orange!
They succeeded far beyond their expectations, finding traces of the Moon's dramatically violent past. This is the story of how the Apollo program developed a vehicle that could drive around on the Moon, collecting rocks and soil that revealed billions of years of history. From time immemorial, people have cast longing glances at the Moon and wished for a chance to travel there. The first person to make that dream come true was the brilliant rocket scientist Wernher von Braun. He led the Apollo program, which actually landed men on the Moon. A decade before the start of the Apollo program, von Braun's conceptualizations of space development were carried in a magazine. At a time when it wasn't even known if humans could traverse the distance to the Moon and back, his blueprints for space development were bold and detailed. Each and every conceptual drawing overflowed with von Braun's enthusiasm for space travel. Exploration on the moon's surface was also included. A major role was to be played by lunar rovers. They were to function somewhat like the covered wagons that blazed trails through the American West. Clearly, even before space travel began in earnest, a lunar vehicle was conceived of as essential to exploration on the moon's surface. The latter half of the 1950s saw the start of a space race between the United States and the Soviet Union. These two superpowers staked their prestige on efforts to launch artificial satellites. In 1961, the Apollo program was launched, with von Braun playing a central role. The next year, development of a lunar vehicle began. Its construction proceeded in tandem with development of the Apollo rocket engines themselves. The best regarded prospect from that phase of development has been preserved. The MOLAB, or Mobile Laboratory, built in 1964. The tires were huge. The vehicle was 9 meters long and weighed 3 tons. The inside was spacious. The design permitted 2 astronauts to live and work there for 2 weeks. The steering wheel and foot pedals were the same size as in an ordinary passenger vehicle. Development was spearheaded by 2 representatives of America's largest auto manufacturer, Chief Engineer Ferenc Pavliks and team leader Samuel Romano. Development went smoothly, but this rover never made it to the moon's surface. The problem was that massive body. NASA realized that they would need another rocket just for the rover, in addition to the one carrying the astronauts. In 1966, the year before the scheduled first trip to the moon, development on the lunar rover was suspended. It was a setback, but the developers waited for another chance.
Our job is laid out for us. Our task is laid out for us, yeah. Well, we didn't have any problem. We didn't think that we couldn't do it. It was our job to get it done, and we got it done.
In March 1969, faced with the upcoming launch of Apollo 11, the 2 men went to inspect the completed lunar module, or landing craft. They knew that their only hope of getting a rover onto the moon would be aboard the lunar module. But the lunar module had no space to spare, except for one unused compartment they spotted. It was a recess just 1.5 meters square and 0.9 meters deep.
Well, when we first saw this is impossible. We can fit this larger vehicle in that space.
But Pavliks, the engineer, did not give up. He tried to see how compact he could make the rover. To carry 2 astronauts, it had to be at least 3 meters long. To get around on the moon's rock-strewn surface, it had to have large tires. But any way they calculated it, it was too big to fit on the lunar landing module. Was there no way to get it onto the lunar module? For 3 months, they experimented with mock-ups. Then, one day,
it's usually these ideas come very suddenly, you know. Eureka.
what was this sudden inspiration? Pavliks demonstrates with a 1/6 model.
Then the seats must be folded down. Then the front chassis, which is hinged, is folded over 180 degrees. Then the same way the rear chassis is folded up. Then the wheels are folded in to the 45-degree angle. And then the complete assembly fits into that triangular shaped envelope, which is between 2 legs of the lunar landing module.
It was ingenious. A foldable vehicle was a huge step toward including a rover in the moon landing mission. Two weeks before the scheduled launch of Apollo 11, the two men took their model to NASA for a demonstration.
When we went to Huntsville, and the engineering people were very excited that, hey, maybe this could work, okay? So one of the engineers said, why don't we show it to Dr. von Braun, who was the director of the Huntsville NASA organization.
Von Braun had the final say on lunar rover development. They had to arouse his interest and enthusiasm. Pavliks had an idea how to do that.
So he led the way to von Braun's office, opened the door, and I guided the vehicle into his office with radio control, that he couldn't see anybody but this little vehicle coming into his office. And he was on the telephone, saw this little thing coming in, and put the telephone down and said, what is this? And then we walked into the office, explained to him what the concept is, demonstrated all the folding up.
Von Braun listened intently. Then, suddenly,
he slammed his hand on a table and he said, we must do this. We must run a vehicle on the moon. And we convinced NASA to go ahead and do it, and we got a contract to do it.
the lunar rover concept championed by the two men had previously been scuttled. Now they'd been given a second chance. Two weeks later, Apollo 11 was launched. The entire world awaited the moon landing with bated breath. The rehearsals for the Apollo program of putting men on the moon and bringing them back were over. This was the real thing. Three months later, the lunar rover project began in earnest. It had a new and powerful supporter, Saverio Maurea. Maurea was a capable manager who had overseen the successful development of the Apollo program's giant rocket engines.
all they do to send out the next model car, it takes them like 4 years before they're happy with the design and they can finally put one out on the street that's different. We had to produce flight hardware for astronauts in a totally unknown environment in 17.5 months.
Starting with Apollo 11, NASA was planning on about one moon landing every 6 months. Apollo 15 was scheduled to undertake full-scale research on the moon's surface in 1971, just 2 years away. The lunar rover would have to be operational for that mission. The contract required development and production within a mere 18 months. This vehicle would be the first ever to run on a surface other than planet Earth's. It was a tough schedule, but they started development by trial and error. The first requirement was the capability to roam freely over the moon's rough terrain. The lunar rover would be useless unless it could easily surmount obstacles as high as 30 centimeters. The vehicle utilized technologies that were still unavailable to vehicles on Earth. It was an electric car, whose 4 wheels were powered by dedicated motors drawing on 2 silver zinc batteries. The 4 motors put out a combined total of 1 horsepower. That was enough for the moon, whose gravity is only 1/6 that of Earth's. Operation was simplified. The manual controller had steering, acceleration, and braking functions all there at the driver's fingertips. Later, to accommodate the bulkiness of the astronaut spacesuits, the controller was reconfigured to a T-shape, so the driver's hand could rest on it comfortably. The design goal was operational ease. Maneuvering the rover was simple. Tilt the controller forward to start moving. Tilt right, it turns right. Tilt left, it turns left. Pull back to engage the brake. Push the button and pull back to put it in reverse. In test runs, actual astronauts checked out every feature very carefully. It functioned superbly. Everyone agreed development had gone well. Morea, however, spotted a surprising flaw.
Not so much the vehicle itself, but how the man would interact with a vehicle like ours in a 1/6G environment.
But what would it be like on the surface of the moon? No one could predict that. So they tested the rover's seats inside a large airplane, which was flown so as to simulate 1/6 of the Earth's gravity. This is the footage of that experiment. The astronaut flops about and can't get seated. There was no point in having a rover one could not ride. But this problem was solved with a little ingenuity. A 15-centimeter bolt protruding from the floor of the car body. The astronaut could then hook his foot briefly under the bolt, levering himself onto and into the seat. Problem solved.
That was the big one. Simple solution, but big issue. This was not simplistic. This was a spacecraft on wheels.
April 1970. By now, they had reached Apollo 13, but the lunar rover had run into a seemingly impassable developmental wall. The problem? The material and shape of those huge tires. In the vacuum of space, pneumatic rubber tires would blow out. They were simply not practical. What's more, on the moon, the terrain, scarred from the impact of countless small meteorites, is uneven, full of potholes. But in some places, the soil is finely granulated, like powder. The tires would have to do well on that sort of terrain as well. They needed something strong, resistant to temperature fluctuations. They thought of a material quite unsuitable for terrestrial tires: metal.
Should be flexible because it was carrying people, so the ride characteristic had to be such that it cannot be a rigid wheel. So we came up with this idea of making a flexible wheel, making it out of spring material.
So they created 10 types of metal wheels or tires and tested each and every type. It had to be lightweight and suited to any terrain. It also had to give a comfortable ride. This is the one they finally chose. Metal filaments were woven together at 4mm intervals. This was a wire mesh tire.
This wheel is a very good simulation of an actual tire. It yields as you press on it, and it returns, and it has enough strength to carry the weight of the vehicle. So it seemed like it, and it can't blow out.
Romano's team had overcome their greatest obstacle. Where does a wire mesh tire get its strength and versatility? Kazuya Yoshida, who helped develop the Japanese asteroid explorer Hayabusa, ran some tests. He fabricated two 15-centimeter diameter wire mesh tires and attached them to a small testing unit. A rock was inserted in the test bed to create a 3-centimeter high obstacle. How will the tires perform? The test unit easily negotiates the obstacle. When tire meets rock, the tire changes shape to accommodate the rock. That suppleness in the wire mesh tire, allowing it to traverse both rocky ground and softer soil, is exactly what is needed on variable terrain like the moon's. The rover was now outfitted with wire mesh tires. The next step was to simulate lunar conditions for full-scale testing. One trick was to have the rover lifted slightly by a crane as it ran, so it would be 1/6 of its real weight, as it would be on the moon. Only after it passed numerous performance tests was the lunar rover deemed ready. Just 4 months before the scheduled flight of Apollo 15, the lunar rover was packed into the side of the landing module. And NASA was setting a new plan in motion. The moon's surface has both dark-colored and light-colored areas. Up to Apollo 14, the moon landings had all been on the dark areas. They are called seas, and they are flat. That made them relatively safe for landing. But the only kind of rock they could find in such places was basalt. There's plenty of that on Earth. So Apollo 15 would approach one of the light areas instead. The plan was to set the lunar module down near the edge of a dark sea, and then have astronauts set out in the rover for brighter, higher ground. NASA had not yet obtained any rocks from the moon's highlands. July 26, 1971. With the lunar rover on board for the very first time, Apollo 15 took off for the moon. Taking the rover made this an historic flight, one that marked the beginning of true lunar exploration. Four days later, the Falcon lunar landing module set down safely on one of the moon's seas, near a mountain range. They were about to realize the fruits of a year and a half of development. An astronaut held the rope that would release the lunar rover from its cargo bay. Back at Mission Control, the two men who had worked so hard to develop the rover held their breath. The rope is yanked hard, and the rover begins to emerge. All it took was one quick pull for the rover to start to deploy. In just 5 minutes, there was the lunar rover, ready to roll. But then came something unforeseen.
Okay. Got a detent. We're moving. Extraordinary. Negative. But I don't have any front steering, Joe.
There was no front steering at all.
Oops, yeah, it was oops. As a matter of fact, within minutes, I got a call from the vice president from Detroit, General Motors, that what's going on? Can you fix the problem? So it was a high, visibility type of operation.
No front steering could have been a serious setback. But the rover had a built-in feature that saved the day. The front and rear wheels actually operated in tandem in a 4-wheel steering system. To turn right, for example, the front wheels would point right and the rear wheels would point left. all four contributing to the turn. On Apollo 15, the front wheels did not steer when first powered up, but the independently powered back wheels still operated sufficiently for the vehicle to be maneuvered. "40 minutes later, the rover was declared ready to explore the moon.
Ben, this is really a rock and rollin' ride, isn't it? Never been on a ride like this before. Boy, oh boy. I'm glad they got this great suspension system on this thing. Boy.
Average speed, 12 kilometers per hour. The two astronauts riding the rover were just ecstatic. Then, suddenly, they realized they could no longer see the lunar module. Since the moon is only 1/4 the size of Earth, traveling 3 kilometers as they had put them beyond the horizon. But that was no cause for alarm. They had built-in technology that gave them distance and angle to the lunar module. The first ever lunar car navigation system. With no fear of getting lost, they were emboldened to go even beyond the sight lines to the lunar module. On the second day of exploration, they made a great discovery. It was while the rover was en route to higher ground. The two explorers were at the edge of a vast crater.
Okay, Jimmy, let's go to work. Roger. Look at that. Almost see twinning in there. Guess what we just found? I think we found what we came for. Crystal and rock, huh? Yes, sir. You better believe it.
It was a white rock, which they called the Genesis Rock. The highlands were composed of rock that formed shortly after the moon itself was born. Hitherto, the lunar seas had yielded only black basalt. What Apollo 15 retrieved from the highlands was a white rock called anorthosite. This discovery made it possible to construct a scenario explaining how the moon achieved its current shape and characteristics. 4.6 billion years ago, the solar system had only just taken shape. Right after the Earth itself was born, a body the size of Mars collided with it. This giant impact, as it's called, blew a vast cloud of debris out into space. The fragments were gravitationally attracted to each other and fused in a repeated process. The result was the moon. As it took final shape, the moon was covered in magma, molten rock heated by the energy from all those collisions. In time, as the moon cooled, white anorthosite began to crystallize in the interior. With a relatively low specific gravity, the anorthosite gradually moved to the surface, where it formed the moon's crust. So at one point, it is thought the moon was entirely white. Then, however, the solar system was struck by a vast swarm of meteoroids. Impacts on the moon created giant craters. They punctured the crust, through which magma pushed up from the moon's core onto the surface. The magma, now lava, cooled in the form of black basalt. This is how the moon's seas were formed. This account of the formation of the moon is based on discoveries made possible by the lunar rover. In April 1972, Apollo 16 was launched. On this mission, too, the rover played a major role. It scampered easily over the moon's rough terrain. And it covered a total of 27 kilometers, 10 times farther than an astronaut could have walked in the same time period. The lunar rover had proved to be indispensable to the Apollo program's moon-based exploration. Suddenly, it was the last Apollo mission. NASA hoped for a spectacular new discovery. The objective was a gorge, cut into steep mountains. This terrain was far more complicated than any attempted before. There was a good chance some strange new rocks would be discovered. And it was their last chance. So on Apollo 17, NASA sent in a ringer. For the first time, a scientist was aboard. A geologist named Harrison Schmitt. Nowadays, more astronauts than ever before have professional backgrounds in science and engineering. Their expertise is valued for conducting experiments in space. But on the Apollo program, given the extraordinarily complex operational requirements, all the astronauts except for Schmitt were military pilots. Schmitt had been fascinated by space since childhood, but he became a geologist. His chance to venture into space came when he was 29 years old.
It was on very short notice. The NASA and the National Academy of Sciences asked for volunteers for scientists to become astronauts in November of 1964. And I thought for about 10 seconds and decided that I would regret not volunteering, and so I volunteered.
Schmitt had never piloted anything more complex than an automobile, but NASA drummed new operational skills into him. Apollo 17 was the last chance to discover new moon rocks. Capitalizing on that chance was up to Schmitt. December 7, 1972. With one lunar rover and one scientist on board, this was Apollo's last chance. Schmitt was given the responsibility of piloting the lunar landing module. 4 days later, they had reached lunar orbit. The lunar module separated from the command module and began its descent to the surface. Carefully, they descended to a narrow gap between steep mountain ridges. In the end, Schmidt and his crewmates made a successful landing.
Stand by for touchdown. Stand by.
They had landed perfectly in the middle of the valley.
As I step off at the
Surrounded by this magnificent scenery, the normally calm Schmidt could not conceal his excitement.
to all those who made it possible.
Really would be great to go to this valley, this deep mountain valley. It's deeper than the Grand Canyon of the Colorado. I mean, it was a very deep valley. It was splitting the ring of mountains around this large basin called Serenitatis. And it had these young volcanics. It had a lot of a very attractive thing.
Schmidt and another astronaut boarded the rover right away and set off to investigate. They traveled west to a point 3.5 kilometers from the lunar module. Right in front of them was a crater more than 100 meters in diameter. Schmidt's instincts as a geologist told him to focus his attention on this crater.
And I think everybody in Mission Control was excited about it too, because it was so unexpected.
The geologists in Mission Control could not conceal their enthusiasm either.
Light gray material.
Until then, there had been no indication that there had ever been volcanic activity on the moon.
We're gonna have to, that's a key to get it down some cone.
A close look at the sand reveals tiny globs of glass, 0.1 millimeters across. They called it orange glass.
It was a volcanic deposit, what we call a pyroclastic deposit. Certainly people in Japan are very familiar with volcanoes that erupt and give and throw glass and debris around. Well, this had happened on the moon.
The orange glass was created 3.6 billion years ago. At the bottom of a crater made by a meteorite impact, magma spewed forth from the moon's core. A fire fountain sprayed droplets of magma from 400 kilometers below the crust out into the cold of space, where they instantly cooled into globules of glass. Schmidt and his colleagues had discovered irrefutable evidence of volcanic activity on the moon. "36 years later, the Japanese unmanned lunar explorer Kaguya photographed the moon's surface with a special camera. It identified more than 40 locations on the moon where there was sand with the same composition as the orange glass. This confirmed that the moon, like Earth, had seen a great deal of volcanic activity.
We were told later on that without the rover, NASA or the government would have canceled the last 3 or at least 2 Apollo flights. So it was, in a sense, the rovers were saved the last 3 of the Apollo flights, because it was a new element in the exploration.
The riddle of the moon's origin was solved by the Genesis rock and orange glass, and it was the lunar rover that led to these discoveries. It's been 40 years since the end of the Apollo program. But research is still being done on the rocks brought back from the moon. New facts are even now coming to light. Alberto Saal is an associate professor of geological sciences at Brown University in the U.S. He's using Earth's latest technology to study the moon's orange glass. When the magma spewed out of those lunar craters, it instantly formed glass globules that incorporated substances from the moon's core. That makes them time capsules of the very origin of the moon. Analysis yielded unanticipated results. Trapped in the orange glass were some of the same gases that exist on Earth, such as fluorine and chlorine. This supported the theory that the moon came from the Earth. Another completely unanticipated substance was found: water. This was the first ever proof that there was water on the moon. When Earth suffered the giant impact that gave birth to the moon, the fragments of Earth dislodged into space were heated to 4,000 degrees Celsius. It had been thought that all the water would have evaporated. But where had the moon's water come from? Currently, the world's only isotope microscope is being used to analyze the moon rocks to solve that very riddle. Hisayoshi Yurimoto has been conducting research of this sort, including analysis of the Apollo mission's moon rocks. That includes measurements of deuterium, a hydrogen isotope. Amounts differ depending on the type of space object in which they are found. The water in the moon rocks contains from 0.02 to 0.03% deuterium. Comparable amounts of deuterium are found in another well-known type of space object: comets. In the solar system of 4 billion years ago, there were many more comets than there are now passing through. Yurimoto believes that the moon was showered with a huge quantity of comet ice in that era, when the comets passed too close to the sun. At that time, it recouped some of the water lost after the event of the giant impact. Since the Apollo missions, no one has walked on the moon. But plans are underway now for new moonwalks. In 2009, the U.S. launched the Lunar Reconnaissance Orbiter, or LRO. It is parked in lunar orbit 21 kilometers above the moon, from which it photographs the surface. This is an effort to compile detailed information for the next people who attempt to conduct investigations on the moon's surface. This is one of the images captured by the LRO. It's the Apollo 17 lunar landing site. Those spidery lines mark where the lunar rover scudded across the moon's surface. Their tracks remain even now. At the end of one of those tracks, a lunar roving vehicle, no longer roving. The rover was a major player in moon explorations of an earlier era. Now it sits there patiently, waiting to greet new explorers from Earth.
We also now know that Saturn is orbited by over 60 natural satellites. The largest of Saturn's satellites is a moon called Titan. It is enveloped in a thick atmosphere, one filled with orange haze. In 2005, a NASA probe penetrated the veil of mystery and sent back the first images of the surface. The terrain looked amazingly familiar. Black lines branched out over the surface. They looked just like rivers. And numerous lakes were discovered. This was the first time any celestial object had been found with liquid on its surface. The more the probe investigated, the more Earth-like Titan seemed to be. It was at this point that scientists began to suspect that life might be present.
Maybe in the seas, more interesting things happen. Maybe you get self-replicating chemical systems, much like those that are the first steps towards living systems that were deep in our own history. So Titan gives us a whole new set of possibilities.
There's the possibility that maybe there is life on Titan that has somehow found a way to make use of all of these building blocks that the atmosphere is making for it.
However, the temperature on Titan is minus 180 degrees Celsius. Could life really exist there?
Well, how do we know it's too cold? Imagine you're living on Titan and you're looking at the Earth. You'd say, oh, there's a liquid, there's organics, there's energy, but it's too hot.
Titan has both an atmosphere and liquids. Could life exist there? This planetary body, very similar to Earth. Saturn's moon, Titan. Imagine the journey from Earth to Titan. If you could travel at the speed of light, you'd pass Mars about 4 minutes into the voyage. At the 30-minute mark or so, you would pass the giant ball of gases known as Jupiter. Then, some 70 minutes after departure, you would finally arrive at Saturn, surrounded by those beautiful rings. Like Jupiter, Saturn is a large, gaseous planet. Finally, you'd reach Titan. With a diameter of 5,000 kilometers, Titan is about 3/4 the size of Mars. It's a moon the size of a planet. Fully cloaked in that orange haze, Titan's true appearance was not known until the 21st century. (1997) saw the launch of the Cassini-Huygens mission. The Cassini orbiter, equipped with cameras and other instruments, and carrying the Huygens probe, was sent to investigate Saturn and its moons, especially Titan. In 2004, 7 years after liftoff, Cassini-Huygens reached the vicinity of Saturn, 1.4 billion kilometers from the Sun. Cassini then proceeded to enter into orbit around the planet and its satellites, and to commence scientific observations. It took this image of Titan. For the first time, Titan's true features began to show from under that thick haze. The day was approaching when we would finally be able to see the surface of Saturn's giant moon. In December 2004, the Huygens probe separated from Cassini and coasted to Titan. The target landing site was near Titan's equator. What that site would be like, no one knew. Titan's atmosphere is 1,000 kilometers thick. The probe entered it. Huygens deployed a parachute and drifted down, jettisoning its heat shield. This image, taken from a height of 152 kilometers, was Huygens' first view of Titan, which was still obstructed by haze. Huygens was shooting still images as it descended. Its microphone also captured the sound of the wind rushing by. This was the first sound recording ever made of an alien environment. These images of Titan's surface were taken by Huygens from 16,000 kilometers up. Black veins, like the branchings of a river, are visible. It does look as though they are flowing to the mouth of a river. Now, from 8,000 meters above Titan, it looks just like the sort of coastline we're used to seeing on Earth. Finally, the landing. This is an image taken by Huygens just after landing. What look like rocks and pebbles strewn about over a flat plain are actually chunks of ice. The surface temperature is minus 180 degrees Celsius. Atmospheric pressure is a little higher than Earth's, 1.5 bars. The horizon seems blurred by mist. This is exactly like some rocky desert landscape on Earth. High above, the Cassini orbiter continued its observations. In the equatorial region where the Huygens probe landed, Cassini discovered a strange pattern. Some sort of regular striping. Further observations found similar striations covering some 20% of Titan's surface. Ralph Lorenz has dedicated himself to investigating this strange striped pattern. He is trying to solve the mystery of Titan's stripes by comparing them to patterns he finds on Earth. This is the Mojave Desert in the western United States. Lorenz believes Titan's stripes are like the peaks and troughs of desert sand dunes. There are indeed real similarities.
It's remarkable somehow that despite the different gravity, the thicker atmosphere, and the different material that the sand is made of, somehow the landscape ends up looking almost exactly the same as many places on Earth. By comparing the shape of the dune and the interaction with the rest of the environment, we can get an understanding of how these structures formed. And for example, different shapes of dunes form in different wind patterns.
So the goal is to solve the mystery of Titan's stripes by investigating terrestrial desert dunes. Lorenz's first step is to send up a kite with a camera for an aerial overview. He's looking for a place that has a striped pattern like Titan's. Next, he mounts a dune buggy equipped with GPS. He wants to measure the heights of dunes and the angles of their slopes. The shapes of sand dunes change by the minute. Lorenz plants a stake with a streamer attached. In fact, he plants a whole line of them along this slope. This will show what sort of wind creates this type of dune. The wind is blowing from screen left, across a gentle slope. Then it swirls around, as if to carve out that slope to the right. So it's become clear that here the wind flows from the milder slope over and down the sharper slope. Lorenz believes that the stripes on Titan are also wind-sculpted sand dunes. A closer look at that image of Titan's stripes shows ridges with milder and sharper slopes, similar to those in the Mojave Desert. So Lorenz conjectures that the wind on Titan must have been blowing from left to right. The winds blowing on Titan's dunes, however, are thought to be weaker than the winds on Earth. The reason for that is that Titan's gravitational force is only 1/7 of Earth's. A relatively small action can produce a big result. So on Titan, effects similar to those seen on Earth are being produced by mild winds.
Titan is still an active world where, geologically speaking, processes are still happening. And the fact that we can see sand dunes, for example, suggests that the winds that move the sand around are still active, that we're seeing a dynamic planet, much like the Earth.
There was another unexpected aspect to those images taken by Huygens. Look closely at those chunks of ice on the ground. They are reminiscent of stones turned over and over by rivers on Earth. Sharp edges are worn down. They're rounded, like pebbles. So there may well be liquid on Titan. This discovery attracted attention and astonishment. Meanwhile, the Cassini orbiter made a surprising discovery of its own. Black spots and blotches were visible near Titan's North Pole. Radar observations showed them to be lakes, filled with some liquid. They number in the hundreds, and some of them are huge. This is the first time liquid has been found on the surface of any celestial body other than Earth. The lakes are dotted with islands and fed by rivers. But with a surface temperature of minus 180 degrees, any water on Titan would have frozen. What liquid could it be in these lakes and rivers? This is it. Liquid methane. On Earth, it's normally a vapor, but at extremely low temperatures, it condenses into a liquid. Methane melts at minus 182 degrees Celsius. It boils at minus 161 degrees. In the 20-degree range between those two extremes, it exists in a liquid state. The temperatures on Titan's surface are just right for liquid methane. Methane is composed of 1 carbon atom and 4 hydrogen atoms. It's the simplest hydrocarbon, and it constitutes the bulk of the liquid in Titan's lakes. A portion of the liquid is ethane, another hydrocarbon with similar characteristics. Scientists at the Jet Propulsion Laboratory are trying to determine how Titan's methane lakes were created by conducting experiments here on Earth. Christophe Sautan is an expert on bodies of ice found in the solar system. This device is called the Titan chamber. With internal air pressure at 1.5 bars and a temperature of minus 180 degrees Celsius, it reproduces Titan's environmental conditions. Inside is placed a disk of ice, standing in for the terrain on Titan. They then release droplets of liquid methane onto the surface of the ice. The methane disappears immediately, absorbed by the ice, like water being swallowed up by a thirsty earth.
So the big surprise, something we did not expect, is that when the methane falls on the ice, well, actually the methane got sucked into the ice. It gets absorbed. It doesn't run on the ice.
However, if methane continues to drip onto the ice, eventually it begins to pool on the surface. This suggests that wherever there are lakes on Titan, the surrounding ice must be saturated with methane. During its landing on Titan, Huygens measured the concentration of methane. That concentration gradually rose the closer the probe got to the surface. Then, the moment it landed, there was a sharp increase. It is thought that this was due to the heat from Huygens vaporizing the methane that permeates the ice. On Titan, liquid methane acts in ways similar to water on Earth. In June 2012, for example, Cassini observed a strange phenomenon near Titan's south pole. An oddly shaped mass seemed to be squirming about in the atmosphere. It was a cloud, swirling. A cloud made up of methane. On Earth, water is recycled as water vapor and rain. One of the factors prompting this is seasonal change. On Titan, the same sort of mechanism seems to be at work. Titan is tilted on its axis, some 26 degrees off vertical. The Earth has a 23.4 degree tilt. It's another point of similarity. Along with its parent planet, Saturn, not shown here, Titan takes 30 Earth years to orbit the Sun. The tilt of its axis gives birth to different seasons. At this location, Titan's northern hemisphere experiences the long days of summer. The northern hemisphere is warmed, producing rising atmospheric currents. Liquid methane on Titan's surface evaporates and is carried southward. Near the South Pole, it is winter. The methane gas is cooled, condensing into a liquid or even solid state. It can form clouds. Like that huge swirling cloud Cassini spotted. When it's winter in the northern hemisphere, the cycle reverses. Now the methane cloud forms near the North Pole. Underneath that cloud, methane rain begins to fall. Since methane is more viscous than water, its raindrops are larger, with diameters of about a centimeter. But as Titan's gravity is weaker than Earth's, the droplets fall more slowly, about 1 meter per second, like a soft snow on Earth. They soak the icy ground on Titan and form lakes. Wind blows, rain falls. When people could finally see Titan close up, they were astonished at how much it resembles Earth. In 2007, the Cassini orbiter spotted something truly peculiar on Titan's surface. A land formation, some 70 kilometers across, in the shape of a flower. What could it be? Perspective can be gained by combining images taken from two different points of view. A three-dimensional image of the topography emerges. That strange formation turns out to be a rugged mountain featuring a 1,500-meter high peak. There's also a chasm that looks like it might be a volcanic crater. From that, one can infer a formerly active volcano. That volcano has been an object of particular interest to Jonathan Lunine, an expert on Titan's internal structure. He says that the volcano did not spew lava. Rather, it pumped up a mixture of ammonia and water.
One thing to remember is that when water is mixed with ammonia, it can stay liquid down to very low temperatures, down in fact to -100 Celsius. But at that point, within a few degrees of that point, the liquid is actually very viscous. It's almost like basalt. And so if that is what is flowing out on the surface, we would see very thick flows.
Lunine believes that under the ice beneath the volcano, there's an ocean. He came to this conclusion due to changes in Titan's shape. Titan completes its elliptical orbit around Saturn once every 16 days. During that time, it regularly feels the changing effect of Saturn's gravity. In short, it experiences tidal forces. At its farthest point from Saturn, Titan is almost perfectly spherical. But at its closest point, where Saturn's gravitational pull is the strongest, Titan grows fatter. Its diameter alters by as much as 10 meters. Lunine says that Titan can transform so dramatically because internally it is not made entirely of solid rock. Lunine's observations suggest the following picture of Titan's structure. The outer crust of ice is some 50 to 100 kilometers thick. The center is comprised of two types of bedrock. In between the ice and the rock, however, is a layer of liquid water. The bedrock generates heat, says Lunine, permitting the water to remain in a liquid state. This ocean layer is some 300 kilometers deep. Ammonia, present in Titan since its origin, has also dissolved into the water. It is thanks to this ocean layer that Titan can change shape so flexibly.
The interior is warm enough that really only liquid water is a suitable, stable material in that region. So we're pretty sure from the gravity experiment that Titan has a liquid water layer under its surface.
According to Lunine, the tidal forces caused by Saturn in turn stimulate volcanic activity. Tidal forces cause friction along the boundary between the ice and the subsurface ocean. The water heated in this way melts some of the icy crust. It builds up like terrestrial magma and eventually forces its way up above the surface. This ammonia-laden water flows out from Titan's volcanoes like lava. Lunine believes such volcanoes are proof of an underground ocean. Beneath Titan's icy shell, a whole new world lies hidden. Saturn has over 60 moons. Among them are Enceladus, ice-covered like Titan, and Hyperion, pockmarked with craters. Mimas has this huge crater. Those are just a few of Saturn's moons, but they all have practically no atmosphere. Only Titan boasts an atmosphere that extends as far as 1,000 kilometers into space. Actual measurements reveal that this atmosphere is 98% nitrogen. The rest is largely methane. Why is Titan the only one of Saturn's moons with a thick atmosphere? Solving that mystery through experimentation on Earth has been a preoccupation of Yasuhito Sekine. Sekine believes that Titan's atmosphere was generated by an extraordinary mechanism. The mechanism? Collisions with small celestial objects. Sekine is trying to reproduce that effect using a laser. When Titan was first formed, its icy landmass contained about 1% ammonia. So inside a vacuum chamber, a disk of ammonia water ice stands in for the young Titan. The laser beam enters from the left of your screen. It strikes a projectile, which then impacts the ammonia disk. That was the laser shot. gases released by the impact are measured. One is nitrogen, released by the disintegration of the ammonia. Titan's thick atmosphere contains large amounts of nitrogen. According to Sekine's calculations, based on his experiments, repeated impacts by small celestial objects could have produced just such an atmosphere.
タイタンの地殻中にもともと入っているぐらいのアンモニアの量があれば今の 1.5 気圧の窒素の大気を作ることができるということを明らかにしました。重要な点はですね、大きい天体でないと大気を重力的に持てないということです。なので他の衛星たちは同じように衝突は起きたんですけど、それぞれが小さいがために窒素の大気を持つことができなかったと。
For example, Enceladus, one of Saturn's other moons, is merely 500 kilometers across. That is 1/10 of Titan's diameter. Saturn's other satellites are also small, with weak gravitational fields. So even if they've been similarly impacted, they haven't been able to hold on to any atmosphere. But did Titan in fact experience repeated bombardment by small celestial objects? Hal Levison uses computers to calculate the history of the solar system. He has advanced the revolutionary theory that some 4 billion years ago, the entire solar system was shaken by a massive event. Levison argues that when the solar system was forming 4.6 billion years ago, Uranus and Neptune were closer to the Sun than they are now. He inputs the location and size of the planets, and also of the small celestial objects that lie further out. Then the simulation begins. At first, the basic situation did not change much. But some 600 million years later, Uranus and Neptune were suddenly flung to the outer realms of the solar system.
Then out, okay? And that caused the giant planets to slowly spread. It was infinitesimal. You wouldn't have noticed it, but the orbits were slowly changing. And that continued until Jupiter and Saturn got to the point where Jupiter was going around the sun exactly twice. Every time Saturn went around once, and that configuration is what set the whole instability off. Okay, so you went almost overnight from a time when, okay, there was a little bit going on, but not much, to this very violent period where all hell breaks loose.
The smaller celestial objects, shown here in green, had formed a ring at the outer edge of the solar system. But then the gravitational force of Uranus and Neptune violently scattered these objects. The result was that in the period from 4 billion to 3.9 billion years ago, the planets of the solar system encountered a barrage of small celestial objects. During this period, Titan also was hit repeatedly, developing a nitrogen-rich atmosphere. That made it a very special moon.
たった1億年とかそれぐらいの短い期間なんですけど、その間にですね、その 1.5 気圧という膨大な量の大気を作ることができたというふうに考えられます。タイタンっていうのはですね、唯一人類が初めて見つけた生きている天体だというふうに言えると思います。で、地球と同じようにですね、表面で液体が存在して、それが蒸発して雲を作って雨を降らしてというような循環が起きているのはですね、現在の太陽系の中では地球とタイタンだけです。で、その点において40億年前のその出来事というのはタイタンにまさに命を吹き込んだと、生きている天体にしたという意味で非常に画期的な出来事であったというふうに思っています。
1977 saw the launch of Voyager 1. Its mission? To explore and observe the outer planets, from Jupiter to Neptune. This was its view of Titan. It was a close look, but still the moon was shrouded in a thick orange haze. However, even then, one scientist maintained that the haze held the secret to sparking life below. Bishun Khare has been trying to penetrate the mystery of Titan's haze since the early 1970s. He participated in the Voyager mission. He is focused on the haze as being itself a source of life. Khare introduces a nitrogen-methane mix into a sealed flask to simulate Titan's atmosphere. The flask is fitted with electrodes. Now Khare discharges them. This is meant to reproduce the effect of lightning or other energy surges on Titan's atmosphere. It's about 10 hours since the start of the experiment. A reddish-brown substance has become visible inside the flask. Khare claims that this is the very same substance as the haze enveloping Titan. So what happened inside that glass vessel? First off, the electrical surges split apart the molecules of nitrogen and the methane. Their atoms recombine with carbon and other atoms in all sorts of ways, forming a variety of new organic compounds. Analysis showed that some 200 types of organic compounds had been created in this experiment. Organic compounds are the materials out of which our own bodies are made. They are the building blocks of life. It was thanks to Khare's work that Titan came to be considered one of the celestial objects on which life might exist. The Cassini orbiter's close-up observations of Titan have come some 30 years after Khare's experiments. Will they confirm that Titan's hazy atmosphere has in fact given rise to organics? The INMS is a device that measures molecular mass. Cassini has used it to determine the composition of Titan's atmosphere. Cassini's data were streamed back to Earth, where they were analyzed by Hunter Waite and his colleagues. Waite led the team that designed the INMS instrument package carried aboard Cassini. Waite's lab was able to reproduce and confirm Cassini's data by utilizing the same INMS system. They could then analyze accurately whatever molecules or compounds the instrument had detected. The results were astonishing. Rendered in the form of a chart, each of the different molecules identified by Cassini is represented by its own colored area. Various organic substances were created in Titan's atmosphere, ranging from ones with a single carbon atom to more complex ones with 6 or 7 carbon atoms.
When Cassini sent back data, we found out that the upper atmosphere was much more relevant than we ever thought, that most of the chemistry seemed to be going on in the upper atmosphere, that very large molecules were being created in the upper atmosphere, way beyond our expectations. Titan is one of the best organic factories in the solar system.
Bathed in ultraviolet and cosmic rays, Titan's upper atmosphere is continually engaged in converting nitrogen and methane into a rich array of organic compounds. As these compounds collect in the lower atmosphere, they produce Titan's famous orange haze. Finally, they are precipitated with methane rain, onto the surface as well. It's been 4 billion years since Titan's atmosphere was formed. During that time, it is estimated the organics settling onto the surface have created a layer dozens of meters thick. The dunes discovered near Titan's equator are thought to be a large deposit of these organics.
Now on Titan, the sand is made, we think, from organic material, and we think that material comes down and gets built up into sand-sized particles that are then accumulated by the wind to form dunes much like these.
Amidst this accumulation of organics on Titan's surface are substances of vital importance to the emergence of life. That finding was made by a young researcher with a specialty in organic chemistry, Sarah Hurst. Hurst has undertaken a minute examination of the organic compounds discovered in Titan's atmosphere. She's written her own computer program to do that. Based on Cassini's observational data, she faithfully simulates the composition of Titan's atmosphere and produces the same organics. Next, she uses her computer program to determine the molecular structure of every compound.
These peaks right here are the masses of the ions in the mass spectrum data, and then it's the number of carbon, nitrogen, oxygen, and hydrogen in each of those peaks. And so then what the code does is it goes through and compares this information to a list that I've given it of all of the amino acids and nucleobases that we're looking at. So here we have, at 136, we have the molecular formula of adenine, which is 5 carbons, that matches. It has 5 nitrogens, it matches. No oxygen, and then 5 hydrogens. So we know from this that we have the molecular formula of adenine in this sample.
Genetic information for all life on Earth is encoded in DNA. Adenine is one of its 4 major components, or nucleobases, and all 4 have been produced in Hurst's experiments. If these nucleobases combine in such a way that they create DNA, then a huge step forward will have been taken towards life itself. With this discovery, speculation mounted that Titan might actually be capable of harboring life. Life on Titan? It may in fact already exist. If it does, what would it look like? The search is on for the answer. Trinidad and Tobago form an island country in the southern Caribbean. They have a population of about 1.3 million. They also have one of the most unusual lakes in the world. It's called Pitch Lake. It contains not water, but naturally occurring asphalt. It bubbles up from an oil field that lies underneath, creating a lake of asphalt that's 40 hectares in area and 80 meters deep. Strangely enough, Pitch Lake is the site of fieldwork being done by astrobiologist Dirk Schultz-McCook. He thinks that Titan is the best candidate for the location of extraterrestrial life. He's come here to try to envision what life forms on Titan might be like. Asphalt, like methane, is a hydrocarbon comprised entirely of carbon and hydrogen. You wouldn't think this was a substance that harbors life. But Schultz-McCook says it actually does contain microorganisms.
Well, this is one of the few environments where it's similar to Saturn's moon Titan, where we know that we have hydrocarbon lakes on the surface. Obviously, Titan is very cold, so it's still different than from over here. But we do have the liquid methane and ethane, which are also hydrocarbons. And if we can find out what kind of organisms are living here in the asphalt lake and how they adapt to living in the hydrocarbons, we think we can get some ideas to how life could operate on a moon like Titan.
Asphalt contains almost no water.
Did you say that there's microbes in there?
Yes, there's microbial organisms in that liquid asphalt.
In this thing?
In this thing, yeah.
Like maybe 1, 2?
Millions.
Millions?
Yeah.
Genetic analysis identified some 600 new types of microorganisms living in the asphalt. Most are archaebacteria, related to the primordial microorganisms that live in extreme environments.
So for them, actually, it's a great environment, it's a great food source, and basically a never running out food source because it's getting supplied from deep down there.
On Earth, there are microorganisms that can use asphalt for sustenance instead of water. Schultz-McCook is convinced that in Titan's lakes, there must be life forms that exploit methane in a similar way. Another scientist, Chris McKay, holds that the methane lakes on Titan contain creatures so unlike Earth creatures that they exceed our wildest imaginations.
Think of fish living in water and ask them to imagine a bird which lives in air. They probably can't conceive of an organism that is so much denser than the medium in which it lives. Fish move through water by floating. So they would imagine a bird must float in the air.
We humans live in an environment called Earth. We produce energy by causing oxygen and organic matter to interact. That is our lifestyle. But McKay is arguing that on Titan, life forms would be based on a Titan lifestyle that makes use of what's available on Titan. Titan's atmosphere contains minuscule amounts of hydrogen and acetylene. McKay thinks that there may be life forms on Titan that exist by deriving energy from the interaction of those two substances in a methane environment. McKay says that life could very well already exist on Titan.
So instead of being small and round, I would guess that a single-celled organism on Titan might be big and flat, like a sheet of paper, to maximize its contact with the nutrients in this thin soup. So it's living in an environment where there's not a lot of food. So it's got to access the food with a big area. And maybe on this area, it has active molecules. So it's like a big flat sheet of paper with little traps on it to collect food. To that life form, that will be the normal environment.
It was not until the 21st century that Titan's thick veil was lifted. Now that we're getting a closer look, what new discoveries await?
So Titan gives us a whole new set of possibilities, and there are for sure perhaps hundreds, maybe millions of worlds like Titan around other stars. Do those have life? Titan maybe can give us some clues.
If life is found on Titan, humanity's view of the universe will surely change.
The best place for me in terms of finding another type of life would be Titan. Because if we find it on Titan, then we know that it really is too. It's not the same as us. When we go to Mars, we may find life on Mars, but we won't be sure that it's not the same life as Earth. So my best hope would be we find life on Titan, because then I know that we found two completely different types of life. Then I can go on to some other science problem.
There is only one body in space that we know of, other than Earth, that has a thick atmosphere and lakes. Titan. If life is found on Titan, it will instantly increase the possibility that life exists in many other places in the universe as well. We may not be alone in the universe. We may have many comrades. The quest to find out for sure continues. Clues to solving that great mystery lie hidden on Titan.